Okay, in our second video, we are still talking about probability distributions, but this time we're going to be talking about two-way tables and Venn diagrams. So this is just other ways of presenting the information. But what's going to happen here is that we're going to have things where there's possibly more than one outcome that could occur. So basically, you're going to have joint probabilities as opposed to disjoint probabilities. So more than one thing could happen at once. For example, the example that we're going to use, and I would have liked to have actually gotten this survey, with you guys during class. I'm just going to make up the numbers here just because I didn't have the chance. But basically, the idea is we're going to ask a whole bunch of people, are you a dog person? Are you a cat person? Meaning, do you own a dog? Do you own a cat? Well, there's obviously a possibility that people own both. Or there's the possibility that people own neither. Or there's a possibility that they only own one or the other. So there's a possibility here that people could be involved in more than just one category. And so that's what we're going to talk about in this one. So the first one is asking us, what is the probability that a randomly selected student from the class is a dog person, a cat person, both a dog and a cat person? Well, obviously what we're going to need is we're going to need some data. So again, I'm just going to pretend that we had taken a survey, and um, we're going to say that 8 people said that they only owned a cat. Well, if you look at the categories, you can find right here that you are a cat person in that category. But if you only owned a cat, you would own a cat but not a dog. So the 8 would have to go here. And then we're going to say that 16 people said that they only owned a dog. Well, here's the dog category. So it would be straight down. But they don't own a cat. So that would be here. And then we're going to say that out of all the people surveyed, 12 people said, well, they owned both a dog and a cat, which would go in that box. And then let's just say that we know that there's actually 38 total people in the class. So we would put 38 as our total. We could actually figure out how many people don't own a dog or a cat just by adding up the ones that we have and then taking that away from 38. In this case, there would only be 2, and you could figure that out, but that would be the idea. So if you look at it, the way this table works is that there are 20 people in the class or in the survey that own a cat, because you got 12 and you got 8. So there would be 20 total people that own a cat. Some of those own a dog, some of those do not. Perfectly fine. And then in the one that goes across right below that where it says not a cat person, so we have 16 people that don't own a cat, but we also have 2 more people that don't own a cat or a dog. So we have a total of 18 people that do not own a cat at all. And if you look at the right-hand column, the 20 plus the 18 adds up to 38. It kind of needs to. And then we can go across the other way. So if you look at just the dog category right here, there were 12 people that own a dog and a cat, but that still means that they own a dog. There's 16 people that own a dog but don't own a cat. So there should be a total of 28. And then there are 8 people that do not own a dog, but they do own a cat. And there's 2 people that don't own either one. So there are a total of 10 people that don't own a dog at all. And once again, if you look down this row right here, there are 28 plus 10, which is 38 total people. And that's got to add up to the total number of people in the survey. So suppose that we randomly select a student from the class. We want to determine the following probabilities. Let's see how this works. I'll do my best to like circle, shade, highlight something so that you get a general idea of what's going on. All right, so the first one says, we want the probability that you have a cat person or somebody that owns a cat. So we're going to take a look at the cats only row, this one right here, the probability that somebody owns a cat. Well, there are 20 people that own a cat out of the total of 38. So the probability is 20 over 38. And again, that could be reduced. It could be put into decimal form. It could be put into percentage. But 20 over 38 is perfectly acceptable. Then we want to know the probability of somebody owning a dog. Well, you look at the dog part. Well, the dog is this column right here. And there are 28 people that own a dog, again, out of the total number of people in the whole survey, which is 38. So there's 28 out of 38. That's the probability that somebody owns a dog out of our survey. And the next one, part C, you want to know the probability that somebody is not a cat person. So again, find that specific part. Not a cat person is right here. So this whole row is the people who are not cat people. And there's 18 out of 38 of them. 18 out of 38. And then you want the probability that somebody is not a dog person. So we're going to look at the column for not a dog, which is right there. And there are 10 out of the 38. Okay, those are not very difficult because it's taking the entire column and taking it out of the total. But now let's see what happens if we want to add an extra criteria, like in number 3. I'll have to kind of scroll up and down so we can see this a little bit better. But in number 3, it says, what's the probability that the 2 events occurring? So we want to know what the probability of somebody having a cat and a dog is. Well, that only occurs in one specific box. Let's see if I can do like a, oops, that's not what I wanted to do. We'll do like a highlighter. Let's go with like a green highlighter. So we want to know the probability of a cat and dog person. Well, we got to find where that is. So a cat and dog person is this one right here. So there are 12 out of the 38. 12 out of the total of 38 people are cat and dog people. They own both. Now we want to know what the probability of somebody who owns a cat and not a dog. So again, let's find that specific one. Highlighter, let's go with blue on this one. Somebody who owns a cat, so we find the cat one, and not a dog. That's right here. And there's 8 out of the 38 people. 8 out of the 38 total. Okay, and this is where I'll have to start scrolling up and down a little bit. Part C, we want the probability of somebody who's not a cat person, but they do own a dog. So somebody who is not a cat person, but they do own a dog is right here. And there are 16 out of the 38 total people. So 16 out of the 38, that's the probability there. And then the probability that somebody is not a cat or a dog person. So we have to find the column for neither one, and that is this one right here. Scroll back up real quick. Again, not a dog, not a cat. There's 2 out of 38 people that are not cat and not dog people. So again, hopefully that makes sense as to what you're looking at. You just kind of have to be able to read the columns and read the rows so you can find the appropriate thing. So number 4 is asking us a bunch of different little things. Is the cat or the dog person, the probability of the cat or dog person equal to the probability of the cat person plus the dog person? Why or why not? Notice the difference in the verbiage here, though. They're asking us, is the probability of cat or a dog the same thing as taking the probability of a cat person and adding it to the probability of a dog person? We already have the probability of the cat person and dog person. That was A and B from above. So now let's see. Is the probability of a cat or a dog? It only has to be one or the other. So we have the probability of a cat or a dog. Well, that means that I could use, I got a bunch of mess up there, so it's going to be hard to figure out how to, I don't know what to go with here. I'm just going to go with black, I guess. Probably the best. The probability of having a cat or a dog person. Well, let's see. If you were a dog person, you are in this category. Okay, so there's 16 of those. I know it says probably that one says dog, but not a cat, but it only has to be one or the other. They just have to be in one category that has a dog or a cat in it that they have. So then you could have the probability of being a dog person and a cat person because they only have to have one. They don't have to have both, but they do. So there's 12 of those. But then there's also a cat person, even though they're not a dog person. So there's 8 of those. The only category that we actually leave out of that statement is the 2 because that's the people who don't like or don't have cats or dogs. So the probability of having a cat or a dog person is 8 plus 12 plus 16. So let's see, 8 plus 12 plus 16, all out of the total of 38 people. Well, let's see if that equals the probability of a cat person plus the probability of a dog person. Cat person above was 12 out of 38. Again, we did that in letter A in number 2. Probability of a dog person was 28 out of 38. We did that in letter B in number 2. Let's see if these things are actually equal or not. So let's add up this one over here. 8 plus 12 is 20, plus 16 more is 36. So there's 36 out of 38. If we add the 2 fractions on the right, we actually get 48 out of 38, which, if you really think about it, doesn't make any sense. These 2 things are definitely not equivalent. So I'll put the little slash to the equal sign, stating that they are not equivalent. And the question then would be, well, why is that the case? Well, the reason that this is an issue is because up here in our chart, this particular category right here accounts for the people who like dogs and cats twice. Okay, it really gets counted in the dog person column and the cat person row. And that's why there's a discrepancy in adding these things up. There's an overlap there that we didn't necessarily have to account for. So that's why it doesn't work out. And what we'd have to do is we'd have to try and figure out a way to eliminate the overlap. And that's kind of difficult to do, but it can be done using different methods. So in this case, it's because the overlap for the why not. I'm not writing all that out, but it's because of the overlap of the dog and cat people that these don't work out. And the probability of the cat person plus the probability of the dog person being 48 out of 38 makes absolutely no sense because that's more than 1, and you can't have a probability that adds up to be more than 1. So 48 out of 38 just doesn't make any sense. All right, let's look at number 5. Number 5 has this thing which is called a Venn diagram. These are actually very popular in math. They kind of give a good graphical representation of what's going on. So basically, you have this box, and within the box we put circles. The circles basically represent an entire set of events. So you can see that on this circle, I'm going to use, oops, sorry about that. I'm going to use my highlighter here. The dog person, everything within this circle, sorry if I'm not coloring completely within the lines there, everything within that circle is people who have dogs. The cat person, I'll go with blue. The cat person is everything that's within this circle. But watch what happens when I get to here. The color changes because that's what happens when you mix colors. But out here, it's still blue. So what happened was the blue and the yellow mixed because there are some people who like both. And that's that green section in between. So that's basically the intersection. When the 2 things overlap it's an intersection. That is also what is known as the and statement, because that is people who like one and the other one. So we can kind of fill in the numbers based upon what we had above. The people that liked both cats and dogs, there were 12 of. So we're going to fill in this middle part right here. Let me go with black. There were 12 people that liked both cats and dogs, or owned both cats and dogs. There are 8 people that only had cats but not dogs. So we're going to put the 8 in the blue section, because those are the people who only liked cats or had cats but not dogs. And then in the yellow section is going to be the people who only had dogs but not cats. And that was 16 of them. Again, all that's coming from the chart. So now what it's asking us to do is to describe the event cat and dog person. So take the values from the table, we did that, and we're going to describe what it means to be a cat and dog person. Or basically, there are 12 people who favor cats and dogs. So 12 people who have cats and dogs. I'll write out the word and because this pen drags a little bit too much. So that is the and statement. That's the intersection. That's the overlap. That's this piece right here. Now describe what it means to be a cat or a dog person. Well, I could be in this part. I could be in this part, because that is a cat or a dog person, or I could be in the center part. That's also a cat or dog person. It just happens to be that they like both. So basically, I need to add up all of those values. So 8 plus 12 is 20, plus 16 more is 36. So there are 36 out of the 38 people that are cat or dog people. So the difference there is the and statement is the intersection. The or statement is what is actually called a union. So when you have an or statement, here, let's write this down here. An and statement is an intersection, and an or statement is a union. And the symbols for those, the union we've actually used before. We used that when we were doing domain. The union is basically the U. And ironically enough, the intersection is basically an upside down U, or some people say it kind of looks like a lowercase n. But that is the intersection symbol. So an intersection means that both things have to happen. The or statement or the union means that only one of the two things has to happen. But you got to count for all those things that could possibly fit in both categories. All right, one more page. As a matter of fact, I'm going to come back with a third video on the last page, and that should wrap it up.